Welcome back, everybody. So let's consider now a type of set of sentences will be very useful in the upcoming proofs of completeness. So these are the maximal consistent set of sentences. It's essentially what you expect. Recall the definition of inconsistent. A set of sentences is inconsistent if from it you can prove some sentence and also its negation. So that's bad, right? So that's inconsistent. There are, of course, some set of sentences that are inconsistent. If you, let's say, put all the sentences, if you put beta and negative beta inside gamma, then they prove beta, negative beta. That's inconsistent. So yeah, we usually don't like those. And a set of sentences is said to be maximal if essentially you cannot make it bigger. And the way we write that is we're saying for every formula phi, either phi. A set of sentences is maximal if you cannot make it bigger. And by that I mean there is for every sentence phi, either it or its negation belongs to gamma. So one of the two has to belong to gamma. And if you have a set that is consistent and maximal, then you have that exactly one of those two is in gamma. You cannot have both, because if you have both, you will be inconsistent. So if you're consistent and maximal, you must have one of those two, but not both. So you cannot be bigger than that. Okay. So what is an example of maximal consistent set of formulas? Well, whenever you have a structure M, if you consider the theory of M, that is maximal and consistent. So why is that? Well, remember, the theory of M is a set of all sentences that are true in this structure M, right? So for different structures, you're going to have different theories. This is all the sentences, the set of all the sentences that are true in this particular structure. So we know that whenever you have such a set, for every formula, either it or its negation is true in M, right? You're gonna have both to be true in M. If you have one, then you can have the other. So exactly for each formula phi, either phi or not phi is true in M. So that's why you get that the set of all sentences that are true in M is a maximal consistent set of sentences. One observation: if you have a set of sentences, so here sigma is a set of sentences that is satisfiable, recall that satisfiable means that it has a model, then there is an extension. You can make it bigger, you can add some sentence to it, so that you end up with a gamma that is maximal and consistent. Why is that? Well, if sigma is satisfiable, then it has some model M, right? And then if you take the theory of M, that's our gamma, right? The theory of M, since M satisfies sigma, sigma is going to be contained in the theory of M, because M is going to satisfy every formula of sigma. That's how we chose M. And therefore, the theory of M is going to be an extension of sigma, which is maximal and consistent. Okay, so if you're satisfiable, you can always be extended to something that is maximal and consistent. Note that if you have a set of sentences sigma, let's say the sum of groups, satisfiable, then you have many models satisfy sigma, and they are all different, and they all have different theories, right? So if you are sigma that is not complete already, then you can extend it in many different ways so that you're maximal and complete, because you can take, let's say, if sigma was the sum of groups, for each group you have a different theory. Well, somehow the same, but you have many different theories of many different groups. Those are all extensions of sigma that are maximal and complete. What's going to be useful to us to show is that if sigma is consistent, then there is an extension of gamma which is maximal and complete. We know that satisfiable implies consistent, but we don't know the other direction yet. We're gonna know it soon. So we're gonna have to prove this one by hand. If sigma is consistent, then there is an extension that is maximal and consistent. How do we show that? So here is the lemma again, so that we can write a proof. And I guess so the claim that we need to show that if sigma is consistent, then and phi is a sentence, then one of sigma union phi or sigma union not phi is also consistent. So this is the lemma that we're claiming here. If you start with something that is consistent and you have a sentence phi, if you add to sigma one of either phi or not phi, one of those two, you end up with something consistent. It's likely that you can add both and you're still consistent. For instance, if you have the axiom of groups and you add the sentence that says commutative, you get the commutative groups. That's consistent, satisfiable. And if you add non-commutative as a sentence, you get the non-commutative groups. That's also satisfiable. So sometimes you get both are consistent or satisfiable. But what we're saying here is that at least one of the two must be consistent. You can always become a bit bigger and prove that it's consistent. So why is this true? If sigma phi is consistent, then we are done. On the other hand, if sigma phi is inconsistent, we show by this reduction to absurdum theorem right here that if gamma phi is inconsistent, then gamma proves the negation of phi. And this implies that sigma proves not phi. So we claim that this implies that sigma together with not phi is consistent, right? And why is that? Otherwise, if sigma together with not phi proves beta, and sigma together with not phi proves not beta, then we get that sigma proves not phi implies beta, and also that sigma proves not phi implies not beta. But putting this together with that by modus ponens, we get that sigma proves beta alone without not phi, and by using this together with that and modus ponens, we get that sigma proves not beta. So then these two together imply that sigma inconsistent, which contradicts our assumption, right? So this is assuming sigma is consistent. So this one is not right, and that's because of the otherwise that up here. So we get that yes, phi and not phi is consistent. Okay, so what we show here that if sigma together with phi was inconsistent, then sigma proves the negation of phi, and that implies that sigma together with the negation of phi is consistent. And so because if you prove the negation, essentially you can add it to sigma and you don't add anything because you're adding something that is already provable from sigma. So if you were consistent before by yourself and you add something that you prove, you should stay consistent. That's what this proof is saying. Okay, so that proves the claim that if you're consistent and you take one more formula, one more sentence, then what you can add one of these two to make it consistent. Now, what is that we want to show? We want to show that if you're consistent, then there is an extension of you that is maximal and consistent. So how do you prove this? How do you finish the proof? So here, so to be maximal means that for every sentence phi, one of the two must be in gamma. So what are we going to do? We're going to start with sigma, and now we're going to go through all the sentences one by one. We're going to put them in order one by one, and we go through each of them, and we add either the formula or the negation into the set so that we stay consistent. So, and this is assuming we have a countable vocabulary. So let phi 0, phi 1, phi 2, phi 3 be an enumeration of all sentences. Okay, this requires a little observation because we need to be able to enumerate them. And the point here is that if the vocabulary is countable, you have countably many symbols in your vocabulary, plus you have countably many logical symbols because you have the variables. There are infinitely many variables you're allowed to use, so it's infinite, but it's still countable. So the total number of symbols that you have is countable. How many finite words you can write with countably many symbols is only countably many words. You have to kind of figure out how to do it, but you can enumerate them all in some way. And from all the words you can write, meaning strings of symbols, some of them are actual sentences, so you have to restrict yourself to the actual sentences, but you can easily find a way of listing them all, kind of like a dictionary kind of ordering of listing all the well-formed sentences in a list, so that you don't skip any, and they all show up somewhere in the list. So once you do that, now you start increasing your sigma to make it maximal, and you do it like this. So let sigma 0 be sigma, and then you do it by induction. You say if sigma 0 together with phi 0 is consistent. So notice that, by the way, that sigma 0 is consistent. We let sigma 1 be sigma 0 union phi 0. And otherwise, we know that otherwise, since the sigma 0 is consistent, we know that sigma 1 not phi 0 is consistent. So we let sigma 1 be sigma 0 union the negation of phi 0. Okay, so we do one of the two. And we always, whatever we define, we are stay consistent. Right? And then we define like this sigma 1, and then we take the next formula and we define sigma 2, and the next formula and sigma 3, and we go all the way up to sigma n, essentially. Suppose we have defined already sigma n, and then we know that if sigma n, we see that if sigma n and phi n are consistent, we define sigma n plus 1 to be sigma n together with the formula phi n, and if sigma n together with phi, no, the negation of phi n is consistent, we let sigma n plus 1 be sigma n together with the negation of sigma n. So at each step, we add to the set either phi n or the negation of phi n, whichever of the two makes it consistent. And we know by the claim on the previous slide that if you're consistent, you can always add one of the negation and stay consistent. So the whole process, you stay consistent. And then at the end, we let gamma be the final result, right? The union over all n in the natural numbers of sigma n. It's going to be maximal because every formula was added along the way. So for every formula, we added either e to the negation inside it, so it's maximal. And why is it consistent? Well, because if gamma proves beta and it proves not beta for some formula beta, then in the proof, in this particular proof, we only use finitely many formulas, right? Because this is a deduction, a formal deduction. A formal deduction can only use finitely many formulas. So that means that these finitely many formulas must belong to one of these sigma n's. These sigma n's are all nested and getting bigger and bigger. So that will imply that there exists an n such that sigma n proves beta and not beta, right? So some sigma n is going to contain the finitely many formulas that show up in that deduction, but this is not the case. This contradicts sigma n is consistent. Okay, so every consistent set of sentences can be extended to one that is maximal and consistent. So that finishes the proof of this lemma. See you in the next video.